Hello everyone, such a pleasure to be here today. My name is Samuel, and today I'm going to tell you about some real-world applications of the Ruby Fiber Scheduler. All the example code is available online using this QR code link. But before we get to that, I'm going to tell you a little bit about its history of its development. Over 10 years ago, I started working on a DNS server implementation in Ruby, unsurprisingly called Ruby DNS. I wanted to host my own website on a server in my bedroom, and I needed to have a hostname resolved differently depending on whether I was inside my home network or coming from the outside internet. So I created Ruby DNS for this purpose and set it up on my local network. Then everything stopped working. Well, at first my web browser got really slow, and then it stopped working. My DNS server had crashed. It turns out making a DNS server with a single process and thus a single point of failure is really bad for a network environment. Accessing a single website can require tens or hundreds of DNS queries, so if your DNS server is slow, it will cause a lot of problems. I wanted to make Ruby DNS robust and scalable, so I refactored the implementation to use an event machine, which was a popular framework at the time. However, because Event Machine had a totally different implementation of I/O, I had to rewrite my server. Ruby's native UDP interface is pretty straightforward. You create a socket, bind, and receive data. Event Machine is completely different. It uses a different method for creating and binding sockets, and a callback instead of the more traditional interface for receiving data. It made me think about the different models we have for building scalable systems. In this case, Event Machine, but also other proposals like async await keywords, and how they force you to rewrite your code. Do we really want to rewrite everything? It was also around this time I built a Wikipedia DNS server that would fetch Wikipedia summaries and return them as DNS text records. To get the summary from Wikipedia, you need to perform an HTTP GET request. I tried several different HTTP clients to access Wikipedia from within Event Machine, but they all caused unexpected blocking that prevented the DNS server from handling more than one request at a time. Here is a simplified event loop which receives an incoming DNS request, does an HTTP request for the summary, and writes the result back as a DNS response. Because the HTTP GET is blocking, it stalls the event loop, so only one request can be processed at a time. This can result in a backlog of delayed requests which can overload the server. In contrast, a non-blocking HTTP client allows multiple requests to be processed simultaneously, which reduces the chance of any one request getting blocked, thus reducing latency and improving throughput. Because all the primitives provided by Event Machine were different from native Ruby, it wasn't obvious to me what combinations of libraries were compatible or would introduce blocking behavior. How could I know what I could use together without causing issues? I started looking for other options that could help avoid these compatibility issues and found Celluloid. Each actor runs on its own thread, so I could have an actor for a DNS server and an actor for an HTTP client, and they would communicate using a non-blocking message passing. This seemed like a good idea to me, since I wouldn't have to worry about blocking HTTP clients stalling the DNS server. I started rewriting Ruby DNS into Celluloid DNS, but I found that it would occasionally hang during test runs. I started digging into the Celluloid code and found that it was occasionally locking up when starting a server before running a test. I started investigating the link operation. Linked actors tie the lifecycle of one actor to another. If one crashes, the other is forced to deal with the failure. Often the way this is handled is using a supervisor to restart the failed actor. I found the Celluloid implementation introduced a lot of non-deterministic, globally visible behavior. When writing tests, previous state or failures could leak into subsequent tests, and it was very hard to guarantee isolation. I wasn't comfortable with a system that had non-deterministic global state as part of its core design. Celluloid was so complex internally that it was difficult to understand or even know what the correct behavior should be. I wasn't sure if I was even solving the right problems. I didn't feel confident enough to use or recommend Celluloid as a reliable foundation for scalable Ruby applications. Why is it so hard to build something as simple as a non-blocking DNS server that performs HTTP requests? Surely this shouldn't be so complicated. I was frustrated. Ruby did not provide a compelling solution to this problem, and it was such a great language in other regards, so I felt strongly that I wanted to solve this problem and make Ruby even better. I started thinking about what I wanted. I'd invested enough of my time in other people's visions. I didn't want to rewrite my code. I wanted things to be compatible with each other. I wanted well-defined semantics in isolation. I wanted a simple, straightforward foundation for introducing concurrency into my programs. So I took all these ideas, and in 2017, I started working on a new gem called Async, which is short for asynchronous execution. Several months later, after I built the first prototype, I released version 1. The short time frame was part of an explicit goal to restrict the implementation to only the very essential interfaces without having unnecessary complexity or features. In 2018, I introduced a proposal for what is now called the fiber scheduler to add hooks to Ruby so that Async could intercept native blocking I/O operations and transparently redirect them to the event loop. Hold on a minute, what are fibers? A fiber is a lightweight unit of execution that must be manually scheduled. They are used by the fiber scheduler to switch between application code. For example, several incoming requests, each having their own fiber. When a fiber executes an operation that would block, like reading from the network, we can transfer to another fiber, and when the data is available, we can switch back. I refer to this hidden context switch as internally non-blocking because it's not directly visible to the application code. One of the first exciting achievements of the fiber scheduler interface was wrapping multiple concurrent net HTTP requests. This showed that it was possible for existing code to be embedded in the fiber scheduler without any changes. The fiber scheduler proposal was merged in 2020, and we have continued to develop it to include many other internally non-blocking operations. At the end of 2021, we released Async version 2, which has full support for the Ruby fiber scheduler. This was a big milestone, 10 years after I first created my DNS server. So now you've heard about why I created the Ruby fiber scheduler and the kinds of problems I was trying to solve. Let me tell you about how it works. Async is a gem that provides an implementation of the Ruby fiber scheduler interface. It transparently intercepts blocking operations and replaces them with internally non-blocking implementations. We refer to the interface methods which allow for this indirection as hooks. One of the first hooks we implemented, and possibly one of the most important, was waiting for network sockets to be readable or writable. Here is a small example of a non-blocking HTTP request using Async and the fiber scheduler. We use the async block to define units of concurrency, which we refer to as tasks. The top-level async block also creates the event loop, so if you nest async blocks, they will share the same event loop. Everything inside this task executes sequentially like normal code, but the task itself executes asynchronously in relation to other tasks. We can use the fiber scheduler interface to redirect blocking I/O operations like connect, read, and write to an internally non-blocking implementation. Notice that we don't need any special wrappers or keywords. Depending on the host operating system, Async uses a highly efficient multiplexing provided by KQ, ePOL, or IOU ring. This allows for multiple tasks to execute I/O operations which run concurrently. Being able to integrate with existing code is also really important, so we made all thread primitives safe to use within the fiber scheduler. One of the most important operations, joining a thread, waiting for it to complete, is internally non-blocking when performed within a fiber scheduler. This provides an escape hatch for native code which might not be compatible with fiber concurrency. Here we show 3 threads being created. Each thread sleeps for 1 second to simulate some native code. Then we can wait for that work to finish without blocking the event loop, which we expect to take around 1 second. Joining a thread is internally non-blocking and won't stall other tasks. We also support thread mutex, which can be used to implement thread-safe access to shared resources. Here we compute the Fibonacci sequence using a thread and an event loop, which share the same state. Here is where the thread reads the previous 2 values and computes the sum within a synchronized block. And here is where the event loop does the same operation. Mutex, lock, and synchronize are internally non-blocking. The thread-safe queue is another important tool for building scalable programs, and it's safe to use in the fiber scheduler. You might want to communicate between different parts of your program using the producer-consumer pattern. Here we have a thread that adds several items to a queue. Those items are subsequently consumed by a task running in the event loop. Popping from the queue is internally non-blocking. Most network clients need to perform DNS resolution, and the standard libc DNS resolver is blocking, so it can be tricky to support non-blocking DNS queries. But we introduced a hook for this too. Almost any program which interacts with a network will need to resolve a host name to an internet address. Any Ruby code that does DNS resolution will go via the fiber scheduler hook, which in Async uses Ruby's own resolver library. Ruby's resolver library is normally blocking, but because it runs from within the fiber scheduler, it becomes internally non-blocking. This is another great example of where an existing implementation can become event-driven with no changes. It's also common to launch other processes and wait on them, so we added a hook for this too. This hook is used by a variety of different methods, including the system methods, backticks, and process wait, so all of these become non-blocking. Here we have an example that launches 5 child processes, each sleeping for 1 second. Since they are all in separate concurrent tasks, the total execution time is only a little bit more than 1 second. We also introduced safe asynchronous timeouts. In Ruby, the timeout module is often regarded as unsafe due to the fact that it can interrupt code at any point. However, when running within the scheduler, only operations which yield to the event loop can raise a timeout error, which is somewhat more predictable. In this example, we put a timeout of 1 second around a sleep of 10 seconds. Both the timeout and the sleep are hooked by the fiber scheduler. The timeout will cancel a sleep after 1 second and safely exit with a timeout exception. So, with the hooks provided by the Ruby fiber scheduler, we can make existing Ruby code transparently non-blocking. It appears to execute sequentially, but it is internally multiplexing between fibers using an event loop. This is a huge achievement, and I'm really proud of it. So, we've looked at how the Ruby fiber scheduler works and how you can take advantage of it using various non-blocking hooks. But what about real-world applications? What kind of problems can we solve? I'm going to break this down into 5 separate questions. Question 1, how can we handle lots of requests? Falcon is a web server built on top of Async and can help your application handle lots of requests, especially in the presence of blocking operations like database queries and HTTP RPCs. Let's compare Falcon with Puma. Both servers are capable of handling more than 10,000 requests per second. This synthetic benchmark generates a small response of around 1,200 bytes. You can see both servers perform well. The more response data we generate per request, the less requests we can handle per second. This benchmark generates a large response body of about 12 megabytes each. At a rate of 200 requests per second, that's about 2.4 gigabytes per second, which is close to saturating a 25 gigabit network link just from one Ruby process. This might seem pretty decent. Why should we prefer Falcon over Puma? To answer that question, let's look at what happens when you introduce a slow blocking operation. Here is a small application that simulates a blocking operation. We use a predictable sleep to reduce the variability of the measurements. Each request sleeps for 1/10 of a second, so you'd expect about 10 requests per second per connected client in our benchmark. And that's exactly what we see with Puma, which is configured with 16 threads, maxing out at about 160 requests per second. Actually, in this test, I connected 100 clients, so not all of them were actually able to get a response, and we had some timeouts. Falcon has a significant advantage in this case, because it's able to transparently context switch between all 100 incoming connections, and thus it gets close to the theoretical maximum of 1,000 requests per second. This is one of the key advantages of using Falcon. Here is some feedback I received just a few days ago. After porting an IO-bound project to Falcon without any code modifications, it shows outstanding concurrency. I was really pleased to receive that. Unfortunately, Falcon can't solve every problem. And for a long time, Rails followed a request per thread model, which limited our ability to handle lots of concurrent requests. This benchmark shows Falcon executing a database query in Rails 7.0 in comparison to my own database gem. The database gem is essentially 1 connection per fiber, so for 8 connected clients, it serves about 8 concurrent requests. While Active Record assumes 1 connection per thread, because of that, all the requests end up sharing a single Active Record connection, which causes a lot of contention, resulting in significantly reduced throughput. Fortunately, that is about to change in Rails 7.1, with the introduction of a new configuration option to control the isolation of per request state. With this change, we are able to allocate 1 connection per fiber. While it's still unreleased, I expect this to mitigate some of the major performance issues when combining Falcon and Rails applications. You can see that in Rails 7.1, the orange bar, it has a similar performance to the database gem when using the request per fiber mode, and I personally find this very exciting. Question 2, how can we gracefully scale up? As web applications grow in complexity, it's important to be aware of the different parts that limit scalability. Fixed size pools can cause major performance issues. Puma has a fixed number of workers, which limits the number of simultaneous requests it can handle. Active Record also typically has an upper limit tied to the number of threads. But this arrangement can be tricky to churn and doesn't respond particularly well to changing requirements. If you don't provision enough workers, incoming requests will be queued and experience high latency or worse, timeouts. If you over-provision your worker pool and don't have enough database connections, you may be unable to handle all incoming requests. Fixed size pools don't gracefully scale according to the utilization. They are a static assertion about the hardware available and the workload. While clearly there are lots of situations where they are acceptable, I've also seen plenty of situations where it performs very poorly. Unfortunately, there is no perfect solution, but Async and Falcon adopt a different policy called utilization-sized pools. What this essentially means is that Falcon will continue to accept incoming connections, slowing down gracefully as CPU and memory are consumed. The async event loop is designed to ensure every connection gets an opportunity to execute on every iteration. This ensures a better distribution of resources across all connections. So here is a real-world demonstration of this effect. We run Falcon with a single event loop and then make 8 connections. Each request sleeps for 1 second, and all 8 connections can execute 10 requests in 10 seconds. This looks good. This is what it should look like. And this holds true for up to about 5,000 connections on my desktop, at which point the event loop becomes saturated and the latency is impacted gracefully across all connections. Here is Puma running with 4 workers and 8 connected clients. Only the first 4 connected clients can complete any requests. The remaining 4 clients try to make a request but end up getting stuck in the queue and receive no response, eventually timing out. Falcon can help you avoid situations like this. Question 3, how can we respond quickly? Most Ruby web applications are built on top of Rack, which provides the specification for how applications and servers should interact. Rack version 2 generally requires you to buffer the entire response. And for good reason. We are able to catch any errors when generating the response and redirect to an error page. But this also increases the time to first byte, and if the response is very large, it will consume a lot of memory. Today, we're introducing Rack 3, which makes real-time streaming a required feature of the Rack specification. Rack 3 has been in development for more than 2 years, and it was a huge team effort. Falcon is fully compatible with Rack 3, and we also introduced a new Rack conformance test suite to help other servers adopt the new features. You might have noticed we also have a fabulous new logo created by Marlena Lorgeson. When we talked about the project, she told me, "It sounds like you need a vacation," and created this awesome artwork of myself, Jeremy, and Ruby relaxing on the moon. So I'm looking forward to some time off in the future, maybe. Anyway, let's talk about real-time streaming in Rack 3. Here is a simple hello world example. We create a body proc which accepts a stream argument, writes to it, and then closes the stream. We respond with the body proc instead of the more commonly used array of strings. The web server will execute the proc with the underlying HTTP connection as the stream argument, which gives you full bidirectional streaming. We can do more advanced things like streaming templates. In this example, we create a small template which sings the traditional 99 Bottles song. Between each line, we sleep for 1 second while generating the output. We can then return this template as a proc that writes to the output stream. The streaming response can be easily demonstrated by an HTTP client like this. Each line is printed after a 1 second delay. So, streaming templates can be great for time to first byte, especially in the presence of database queries. In fact, this kind of output streaming was a feature of PHP for many years, and has been used extensively to create real-time output. But what other cases are there? Buffering large datasets can require a lot of memory. Multiple requests with pagination are sometimes used to avoid these issues, but ultimately result in more complexity. Incremental streaming of rows can reduce latency and memory usage. Here is an example showing how to stream CSV data using the Rack 3 streaming body. We wrap the output stream in a CSV interface, then we generate rows of CSV data. It's that easy. The streaming CSV can be seen using the command line HTTP client. Since we only generate 1 row at a time, the memory usage and latency is greatly reduced. If we want to stream real-time events to a web browser, server-sent events are a good option. The protocol was first specified in 2004 and supported by browsers starting in 2006. It's excellent for real-time events like chat messages, stock market tickers, status updates, anything you want to update in real time. On the server side, you generate a streaming response of type text event stream. The specification is pretty basic, but you can send multiple different event types. But in this case, we just have one event type called data. We can implement some client-side JavaScript to receive these events. We create a new event source object and listen for all messages with the callback function. We append the message to the document in the callback as an example. Then if we open this page in a browser, we can see the streaming events. It will automatically reconnect if disconnected, and it's far easier to use than WebSockets, so I highly recommend it. Question 4, how can we reduce latency? It's very common to have a web application talk to external systems while handling a request. Here we have a request that performs an HTTP RPC or some other web service which needs to complete before we can write the response back. Often, you'll have more than one external operation, and executing them sequentially can result in a slow response. If we could just rearrange these operations so that we could execute them concurrently, we could significantly reduce the latency. In fact, you can do this today using async in both Puma, Falcon, or even in Sidekick. Here is a simple method which computes the best price for sending a request by sending a request to several shops concurrently. For each shop, we mapped the shop URL to a price by performing a GET request and extracting it from a JSON response. Then we wait for all operations to complete and return the minimum price. We can visualize this and compare the sequential execution, which takes about 1.5 seconds for the total of 4.5 seconds. But if we do this concurrently, it only takes about 1.8 seconds total. Async makes it very easy to implement fan-out and map-reduce style processing, which can greatly reduce overall latency. Question 5, how can we support real-time interactions? Rack3 bidirectional streaming makes it easier to support WebSockets. I created a gem called Async WebSocket which supports this new interface. Here is an example of how simple it is. You can comfortably handle between 1,000 and 10,000 connections per process. After that, Ruby's garbage collection and latency can become an issue. This kind of simplicity encourages experimentation and new approaches to interactivity. This is an example of a web application that renders HTML on the server in real time and streams it to the client. It also streams events back to the server so you can interact with the board and the buttons. You can actually try this application online right now. It's using Rack3 and WebSockets. If enough people connect, maybe we can test out how robust the server implementation is. It's running on a free Heroku dyno, which I think has a limited number of connections. So if it crashes, it might not be the problem of Falcon. I don't know. So please feel free to try it. So in summary, Falcon is a great server for I/O-bound applications. Ruby 3.2 and Rails 7.1 are going to deliver exciting opportunities for concurrency in production. Be careful with fixed pool sizes, especially for servers like Falcon that will push the limits of your application. Take advantage of real-time streaming to reduce latency and memory usage. Look for opportunities to improve the concurrency of your applications. And let's have fun exploring new opportunities for interactivity with WebSockets. Oh, and what about Ruby DNS? I rewrote Ruby DNS on top of Async, and now it's very easy to make your own scalable DNS server in Ruby. So first we start the server, and then we can make a request to RubyKaigi.wikipedia, and we get the response back. Actually, most of this code is very similar to the original implementation from over 10 years ago, but it's non-blocking. So I feel like I achieved my goal. Thank you for listening to my talk. Please come and see me during lunchtime if you have any questions, or feel free to send me your questions on Twitter. I hope this talk was exciting and makes you excited for the future of a more scalable Ruby. Thank you. Presentation.